Okay, so today we plan to have some kind of discussion about simulations of gravity systems or black holes. I guess I say a few words and hopefully you will interrupt me and correct me, and we'll have some kind of conversation of where this is going. Now, before we start, I would like to invite everyone who would like to come to a dinner tonight at 6:30. We'll be at some local restaurant. And if you want to come, you just email Lisa. Here is the email address before 2 p.m. today. Okay, so I mean, we think we have examples where certain black holes can be represented. Well, we think that in general black holes can be replaced by a quantum system, that they are described by quantum mechanics. And by quantum system, we mean some system of qubits with some Hamiltonian acting on it. And this is supposed to hold for black holes in nature in principle. We, of course, haven't tested this idea for black holes in nature, but we have some perhaps toy models or simpler situations where we think we know both black hole and the corresponding quantum system. Now, when we depart from the theory of nature, we start discussing this in more generality. We can discuss various theories of gravity. So we can talk about maybe we have the Einstein action, maybe we have some magnetic fields, and so on. And when we discuss these examples, we should say, well, what kind of theory of gravity we want. And I think we could restrict to examples where something like Einstein's equations are valid. So we have the Einstein theory plus perhaps some other fields, a relatively small number of other fields. And for that, we would need that the area of the black hole in Planck units. So the Planck scale is determined by the Newton constant of that gravity theory. And we're talking about gravity theories in general. All that matters is this dimensionless quotient, which is related to the black hole entropy, so equal to black hole entropy. And we want this to be much bigger than 1 in order for gravity to be valid. So this is kind of a necessary condition to find something like this. Now, so in particular, if we have some number of qubits, so the number of qubits should be somewhat bigger than S, and this in particular should be much bigger than 1. So that's a necessary condition for having some system like this. Yeah. Now, if we discuss in more detail the type of Hamiltonians that we expect should be related to this type of system, we find that we not only need a large number of qubits, but we also need that they interact sufficiently strongly with each other. So maybe typically we might have some all-to-all interactions, but they can be k-local. So we could have 4 local interaction where you have, let's say, 4 qubits at a time. But those interactions have to be suitably strong. So we couldn't have this in a weakly coupled system or in a nearly integrable system. And that translates into, again, some validity of the Einstein theory. So the Einstein theory is special because it has a light or mass, but has a massless spin-through field, but there are no other light higher spin fields. So we don't have light, let's say, spin-4 fields that interact with gravity. And so the condition that we don't have such fields typically implies that this quantum system should be strongly interacting, at least in the examples we understand in more detail. Now, what examples do we have? So an example that's been discussed a lot recently that probably all heard of and maybe are all familiar with is the SYK model. I presume I don't need to tell you what it is. And now that that's a model that has n Majorana fermions, and we can only take the Larsen limit, and there are some things we can solve exactly and analytically in the Larsen limit. And the physics of this model has some aspects in common with near extremal black holes, with a kind of black hole that we could consider. Do I need to explain to you what near extremal black holes are?
Or you say one word.
Yeah. Okay, so these are black holes that. So let me first tell you about black holes in flat space. So when you have a black hole in flat space. Okay. So near extremal black hole is a black hole that in the near horizon geometry has a particular geometry called ADS2. So the radial and time directions combine into a two-dimensional space with constant negative curvature, which is called ADS2. And that implies that the system has a certain sort of scaling symmetry. So it's a quantum mechanical system that develops a scaling symmetry at relatively low temperatures. That's a feature of the SYK model. Near extremal black holes are such that the geometry has this form, and the isometries of ADS2 are related to this scaling symmetry that emerges in this quantum mechanical system. And a lot of the physics that is common between SYK and ADS2 has to do with the breaking of this symmetry. So some subtle breaking of this symmetry, and this implies some very generic and universal properties. Actually, both systems. So they share the symmetry that governs a lot of the dynamics.
Wouldn't you say this one has light higher spin fields though, because of the fermions?
Yes, yes. So the things that they have in common are related to the emergence of this symmetry, but we think that in the bulk, this ADS2 geometry, we don't have local Lagrangian, so some local fields with very local interactions. So we think this example is probably more similar to an example with higher spin fields than it just said. So, that's a reason why we are not totally satisfied with the SYK model as a model for black holes or something which has a local space-time Lagrangian in the bulk. Okay, so now the SYK model is has many random couplings, and it's in some sense generic within its class of models, in the sense that you just say that you have n Majorana fermions and you have, let's say, time reversal symmetry, and you consider the leading interaction at low energies, you will have the 4 fermion interactions, and you have some random system because there are these 4 fermion interactions are random. So in some sense, it's a generic model, at least within some measure. On some other extremes, many of the examples that we have are very on some kind of complete extreme. We have very ordered models, so very, very symmetric models with lots of symmetries. And where the symmetries constrain a lot the form of the Lagrangian and also the form of the dual gravity theory.
So maybe one question about the SYK.
Yeah.
So is it that just you study SYK and then all of a sudden it turns out that it's very similar to the black hole? Or is that you started thinking about black holes that could be the model that would, and then you make the association and then it came out?
Well, yeah, so
or is it just a simple example that turned out to be like that? And
well, you're asking me a bit more historical question. So this symmetry of near extremal black holes was identified a long time ago, and when people started studying this, Sachs noticed that it was similar to some models that he and had worked on before, that symmetry was similar. And then Kitaev simplified that model a bit more and did some other calculations with the model, understood better the low energy dynamics. And and then people studied it more intensively.
But this was related because some properties were identified for black holes appear in some other models.
Yeah, exactly. So for example, the main observation such that was that this scaling symmetry that you see in this two-dimensional theory arises in the model they consider. And they were studying these models because of some motivation from condensed matter. Also in the context of ADS, CFD, and holography, they were also studying geometries which could possibly be related to these condensed matter systems. And eventually they identified that the ADS2 geometry was relevant for many of the phenomena they were interested in studying. And then the connection was made. Simpler model.
My understanding was that Kitaev wanted to make a model that had the fast scrambling exponent.
Yes, that's a new one.
So that was inspired by black hole. He said, I want to find a model that does this. I don't think
Yes.
Sakdev knew that it has the.
No, he didn't. Yeah, so he did more.
Yeah.
So Kitaev did more calculations with this model and understood in particular this maximal scrambling property that was not understood before. Okay. So I could give you a flavor of these models that really do have an Einstein gravity dual with the local back Lagrangian. I think Ignacio wanted to hear more about this. We could go in this direction, or maybe we could have some discussion at this point. Yes.
Can I ask the quantum computing people question?
Yes.
I was gonna, how hard is it to simulate K-local Hamiltonians that don't have any kind of lattice interactions? Because that's the key bit for SYK, for simulating SYK on a computer. And like yesterday, almost all of the discussion was about lattices, not things that have like heavily non-local interactions.
If you have a fault-tolerant quantum computing would not be more difficult than a local theory. If you have an analog quantum simulator, it will be extremely difficult because the interactions in nature are local, and in order to engineer non-local interaction, you have to put cavities, photons, and so on, and then there are many losses, so it's not very reliable system. So
even quantum simulating SYK is extremely hard because of the fact that it has like no locality at all.
well, it's hard going beyond 5-10 particles. You would like to go to a million particles or 1,000 or something like that would be hard without having some dissipation that would probably.
What if you're at finite temperature? Like part of the point of Lucan made this point, if you're willing to have finite temperature, like if I have my errors are not systematic, then you can have many more qubits. If I'm willing to have finite temperature and how far can I get?
Well, I think that would be very difficult to be lucky such that your dissipation corresponds to some final temperature in your system. So,
But this is a temporary problem, though. I mean, like you said, once you have a real quantum computer, it's not hard. It's for a theoretical quantum computer, it's not hard. Not the ones we have right now.
Well, yeah. Theory and experiment are the same, but.
No, but some things are hard in theory, right? Simulating on a classical computer is hard in theory, right? And simulating on a quantum computer is merely hard in practice.
I guess I was asking about the near term, but that was just somewhat.
Well, I think we touched upon one question that I guess is interesting, which is that if we want to simulate a black hole, we're trying to simulate the system at finite temperature. And the question is whether maybe some errors can be similar to finite temperature or not, or we could maybe we don't need as much precision as to simulate, some more complicated task that requires us not to make any errors. Because that's the question.
yes, indeed, in quantum simulation as compared to quantum computation, in quantum simulation, sometimes you're interested in some K-local observables, not in the whole many-body wave function. And then the errors are not so important there because the errors, you flip one qubit here, but you're measuring the quantity here, it doesn't matter. And so that's when you take that into account, then it seems that it's not so difficult as general purpose quantum computation. Quantum simulation should be simpler.
Yeah, I guess, yeah. So the question is to what extent are these errors similar to finite temperature, I guess.
or the disorder averaging. The fact that it's a disordered system. Would that help? Would imagine.
You mean like in SYK?
Yeah, the noise could be the disorder to some extent.
Yeah. Yeah, I guess it depends on the question you're asking.
So can I ask a question about this disorder? Because the disorder is chosen randomly.
Yes.
But on the ATS or on the geometric side, are you now thinking of an ensemble of series or that, and it's just kind of a typical instantiation, or is the whole choice of the randomness of the disorder integrated into the series? Or how should I think of the randomness of the disorder?
Well, it's that's a very good question for which we don't have a good answer. At least I don't have a good answer. There are, it looks like depending on the kind of theory you consider here, the theory might correspond to a disorder average, or perhaps if you consider more detailed. So the idea is, let me say we don't understand it very clearly, but roughly the idea is the following, that if you are dealing with the disorder average, this theory here will be fairly featureless and have perhaps no matter. And you start considering a specific case, maybe there will be specific instances of matter here. This is how it might work, but there are specific types of interactions. But as you specify more and more, you have more specific interactions. But we don't know whether that's the right picture.
So it's partially an open question.
Yeah, I would say we're in the process of understanding this. I don't know, maybe other people.
I have a really question for the randomness. So say, let's imagine we can realize some simulator, we can realize some audio coupling. But the coupling constant usually cannot be made really random, right? So for example, say let's imagine I can tune your cavity or whatever, you can make the coupling to be kind of a random, like a random distributed, like a Gaussian. But for each term, it may not really like Gaussian, right? What I mean is, for example, you have like all the terms, like you put everything total, the statistic looks like a Gaussian. But if you look at like coupled to like psi one, all the terms coupled to psi one, they may look like a Gaussian. So somehow, in theory, I think we have not really understand like how to study the simulation away from the Gaussian randomness. And not accurately, like every coupling constant is independent Gaussian. Right? If it's not independent Gaussian, what's the effect that we may see?
Well, I don't know very well the answer to this question. Some other people might know it better, but my impression is that you can, in the particular case of SYK, it's likely that you can have maybe non-Gaussian things like only plus and minus couplings and have similar behavior, perhaps. I mean, in other models like the SK model, the Sherrington-Kirkpatrick spin-glass model, for example, you can have couplings which are plus and minus one and get something similar than continuous couplings.
Okay.
So there, but yeah, so that's what I know. Maybe someone here knows more about this question.
Yeah, I just wanted to make a comment that there also, it's familiar to many people here, but not to everyone, probably, that there are non-random models that are very similar to SYK. And for a large enough n, they are also expected to have a huge number of closely spaced states, like the model that Witten pioneered.
Yes.
It's also like a large assembly of Majoranas, but coupled with specially chosen fixed interaction.
Yeah, so again, there are models that have, okay, you already said. Yeah, so there are models which have more symmetries and very special interactions, so have similar physics. Okay, so so I think we could discuss an extreme case here of a very symmetric model that people had studied a lot in the, let's say, string theory community. And just to give you a flavor, perhaps, of what a model where we know more precisely what the gravity dual is, just to make the discussion a little more. Is that okay? Yeah, so before I discuss that, let me like to say a few preliminary things, that's what elementary things. So we're interested in interacting theory. So let's first discuss the free theory. So this is a harmonic oscillator. So you all know the action of a harmonic oscillator. And now we'll introduce an interaction. So the interaction will be g squared x to the fourth, right? That's a simple interaction. And my only point here is to point out that this interaction has dimensions of energy cube. So this is something more or less clear. So this is something elementary, just counting the dimensions and so on. So what that means in particular, for example, is that if you look at the ground state energy of this system, the energy would scale like to the one. So this will be the scaling of the ground state energy for as a function of g squared when g squared is very, very large. By very, very large, what I mean is that g squared is much larger than omega cube. Right? So in this regime, that's the strongly coupled regime. So there, when we look at the ground state, we can't approximate it as a harmonic oscillator. We really need to consider this quartic interaction. The quartic interaction is not a small perturbation, it's dominant. And it's what will give us the scaling of the energy. Okay, in general, this will be a function of the g squared omega, but in this regime, it will scale. And not only that, but yeah, so when we're in this regime of very strong coupling, we have a kind of, so if we replace this, there is a kind of scaling symmetry of this Lagrangian. That is, it's classically, if you forget about the overall normalization, we can rescale of the terms of some constants. Okay, so that's a simple Lagrangian. Now, you could consider an interacting system that contains many harmonic oscillators. And now, in addition, so these many harmonic oscillators interact with some order one couplings, Xi, Xj, Xk, Xi. Okay. So this is a more general version of the same thing. What I said before about the scaling of G and the energy one third, I said that that's essentially the same. Okay, now we will discuss some systems where we choose very special coupling. So it will be a special class of systems of this kind. Okay, so a special kind of system is one in which we can arrange these interactions in terms of a matrix. So we'll define X, let's say 1, 1, so this is one harmonic oscillator, X1, 2, X1, N, X1, X2, 1, etc., up to X and N. Okay. Here, this we're not doing anything, we're just simply arranging all the N square harmonic oscillators in the matrix. And the only purpose of doing this is that now we can write down the Lagrangian as the integral trace m dot square plus omega square m squared, right? So here, this is just the action for all the harmonic oscillators individually. We haven't done anything yet. But then we can add an interaction which is g square m to the fourth, okay? So this is just the matrix multiplication. So we multiply all these matrices, and that will lead to a particular interaction roughly of this kind between all the harmonic oscillators.
Is M a symmetric matrix?
Yeah, we can take M to be, let's say, a Hermitian matrix. So this will imply that these are real and these are complex conjugate. That means it's a pair. But yeah, it's not very important. Well, it's important for the details, but not conceptual. Okay, so then we can consider this particular model. Now, what we said here is essentially similar. There are some powers of n that appear in this discussion. So they are like this. So this is just some n counting, which comes from thinking about how many n's appear in the interactions. So that the ground state energy of this model will be of this order, same scaling with energy. The 1/3 comes from just the scaling with energy. That's again in this particular regime. Okay. Now this model is actually particularly simple, so it can actually be solved exactly. So it's due to some. Oh, one more thing. I forgot to mention one thing. So this model has a global symmetry, and they're changing M to M U minus one. So this is U is a unitary matrix, and if we do this change, then this Lagrangian U is a constant matrix independent of time. So Lagrangian remains invariant. So it has this UN symmetry, and we could restrict to UN invariant states. So that's also similar to saying that we are gauging the symmetry, but that word that confuses you, just think of restricting to the UN invariant states of this model. And if we consider that problem, then it is exactly solvable, and it was discussed in the early. Well, it was discussed, I guess, first maybe by.
It would be sufficient to restrict to UN invariant observables, or?
Yes. Also, we restrict to so
but
consider
just-
UN invariant states and UN invariant observables. And UN invariant observable, for example, is we compute the trace of m squared would be as a function of time, or maybe 2-point functions of the form trace m squared at different times, one at time equal to 0 and the other at time equal to t.
But
These
if you
are
restrict,
examples of UN invariant observables.
but if you restrict to those type of observables, you don't need to gauge explicitly the symmetry. Is that right?
No, yeah, it is more or less equivalent to saying that we restrict to these observables and or that we're gauging the symmetry. It's essentially the same. Okay, so that's
So this expectation value is a finite temperature or zero temperature?
yeah,
or
you
is it-
could consider either. So finite temperature or zero temperature, and you could do this. Unless you are curious, I won't tell you what the answer is, how you solve it. So there is some technique for solving this.
Is the ground state also UN invariant?
What?
Is the ground state UN invariant?
Yes, in this case. And yeah, and then well, it's kind of intuitively clear because it's like normally when you have rotation symmetry, the ground state is rotational invariant.
Oh,
Non-rotational invariant things have more energy, and that's true in this case.
okay.
But if omega squared is negative, maybe.
Oh, yeah.
Well,
That's some sugar.
yes, there are a few things, but I think it's true fairly generically. Even when omega square is negative, or even when g square is negative. I wasn't very careful about the signs here. I guess maybe I should. Well, yeah, sure.
It's Lorentzian.
Now if we are.
You're in Euclidean signature.
Well, okay, yeah, I could take that intended to be Lorentzian. Okay, unless you ask, I won't say exactly how you solve it, but the thing is that it is exactly solvable and there is some connection to gravity, but because it's exactly solvable, that gravity theory doesn't have really properly behaved by black holes. So not that interesting. But we think that as soon as you add one more matrix, then we think it will not be solvable. And this matrix, there are two matrices that are interacting with each other, probably won't be solvable. And maybe that model might or might not have black holes, we don't know. Models with two matrices. What we do know is that models that have lots of matrices are, well, by lots, I mean 9 matrices.
So when I'm
So we
correctly,
jump,
you say
yeah.
that if you have two matrices
Yes.
already,
Yes.
there would be a question that it's not solved or you cannot.
Yeah, we cannot, for example, calculate the ground state energy of those correlators we discussed in those models with two matrices.
When I was a student, Steve Schenker told me if you can solve the two matrix model, you can solve the world.
Yeah.
You agree? I haven't solved it, so I don't know.
Well, he certainly would agree that if you can solve this 9 matrix model, then you
Yeah.
can solve the world because he had the theory of the world. What we discussed. So,
have to go to the 16 fermionic matrices.
yes, I'm skipping that bit, but let's discuss the fermions, which are not as scary as this one. So even, yeah, let's discuss the fermions before we get to that, so. We could consider Lagrangian, which contains some fermionic fields, a complex field, or well, it could be a Majorana fermion. So let's say we have a Majorana fermion. And if we have a pair of Majorana fermions, right, that's the thing of having a qubit. And if we have many Majorana fermions, then in principle we can do Jordan-Wigner transformation and make it into batch qubits, so it's not more complicated than anything it's normally discussed. Of course, there is some overhead in the Lagrangian that looks simple in terms of these fermions, maybe a bit more complicated once you do the Jordan-Wigner transformation. I presume I don't have to say more about this. It's clear to everyone. So you can think of a model which has fermions as well, a bunch of harmonic oscillators plus some qubits. They could interact with each other, so we could have terms that equal psi1, psi2, let's say x, something like this. And the Lagrangian will discuss as these terms. So the theory we are going to discuss has some matrices and I runs from 1 to 9. And then some, again, Majorana fermions, psi A, which are, let's say, psi alpha goes from 1 to 16. And each of these are n by n matrices. So it's just saying it's just a collection of them. So we have n squared individual elements here. And this times 9 for the bosons, and this n squared times 16 for the fermions. Okay. So some level is just we have some kind of collection of harmonic oscillators and fermions, qubits that are interacting with each other. So it's not more complicated than that. So, and the interaction is similar to what we discussed previously, m dot squared I. So now we have the sum over I, which goes from 1 to 9. I've not written explicitly. And then sum over I and j, something which looks commutator of the two matrices, squared. So this is, you take the matrix oscillators, you take this commutator, it's just some particular combination of oscillators, and you take the square of that. So it's a potential that is positive definite, so we don't have the problem that we have this oscillator going. I mean, the energy decreases, it's a positive energy Lagrangian, Hamiltonian, let's say. And,
Sorry, so the matrices are not independent. Let's say, how many variables? There are n squared times 9 or n squared variables that appear in the different matrices?
N squared times 9 variables. Yes.
And they don't commute with each other?
They commute with each other, but of course, the m dot, the momentum conjugate, and they don't commute with the.
But the mi and mj?
Well, the matrices don't might not.
Sorry.
Yeah.
Okay.
Yeah, there are two notions of commutativity here that should not be confused.
Okay.
One is the fact that they're matrix and we can multiply them, and they don't commute as matrices. But as quantum operators,
multiplying the matrices and taking the other order, and
all the elements as quantum operators commute with each other, but the elements of m dot do not commute with the elements of m as operators. Yeah, sorry about that. This is just a way to write it. So some particular interaction similar to what we discussed here, with particular CIJKs, right? But this is just a convenient way to write it that makes manifest the UN symmetry. That there is all these matrices can be conjugated by UN, the same U for all the matrices, and then this will Lagrangian. And then we have the fermions. And this is again a matrix commutator. Now this might look complicated, but it's really simple. So the alphas are spinor indices and they're SO9. So the Lagrangian also has an SO9 symmetry, so we can make an SO9 rotation of the matrices. This is in addition to the UN rotation. It also has a UN symmetry or SUN symmetry. Yeah, so this term is invariant, and here these guys are just some spinor index, some other representation, and this is some gamma matrix which transforms one representation to the other, so that this whole thing is invariant and there is SO9. So this is the Lagrangian, so it's relatively simple. We can write it explicitly. And then, well, we could put here a G squared. The form, as we said, this Lagrangian has many symmetries. So we discussed already two of the symmetries. And in addition, it has this so-called supersymmetry. And this is some symmetry that relates these sonic and fermionic variables. And it implies in particular that the Hamiltonian is the square of some other operators. It's a formula roughly like this. And I don't know whether this helps for the quantum simulation. It might help. I don't know. But there might be a question whether it's simpler to do this. But this is, I think, not very important question. Okay, so now what's the claim to fame of this Lagrangian? Well, why am I discussing it? The reason is that this Lagrangian is supposed to be related to a certain 10-dimensional black hole. Okay. So it's a spherical symmetric black hole. So when we consider this system at finite temperature, we have a 10-dimensional black hole, which is a solution of a very specific gravity theory, which is the 10-dimensional so-called type 2A gravity theory. Type 2A supergravity theory. So it's a particular gravity theory that contains various fields. Its action contains 1 over T Newton times curvature and maybe a scalar field. Well, not maybe, definitely contains a scalar field and some Maxwell term. And then there are some other fields that will not be important for what I'm about to discuss. So it's a Lagrangian that contains a few fields. Some of them are similar to the fields we have in nature, like the metric or one gauge field. And then we also have this theory of fundamental scalar field. And this is a charged black hole. So it's a black hole that carries charge under this U1 gauge field. So there is some flux of electric field. And the flux of the electric field, the integral of the electric field over the sphere. Yes, over the 8 sphere far away. That's some integer n, which is the total amount of quantized electric charge. So that's a black hole that is a solution of this theory. This black hole in principle has this charge and can have any mass. Okay? But as you take the mass close to the charge, you go to this extreme element, the geometry develops a region near the horizon that roughly speaking looks a bit like this. So it has a kind of scaling symmetry. It's not quite scale invariant, so not different from ADS2, but somewhat similar in the sense that as you scale down, the space becomes a little bit bigger. Kind of scale, let me call it covariant way. So it's the equations of motion are scale invariant, but the action scales by another constant. So almost scale invariant, let's say. So you can take this.
So one question here. So here is classical gravity. So
Yes, so this Lagrange.
it's an action for classical field theory for the gravity, but a quantum field theory for the rest, for the.
Yeah, so let me clarify that. So when n is very large, in principle, the duality involves the full quantum gravity. So not just classical, but the full quantum gravity theory. And it also involves what's called the type 2A string theory. So also strings and so on. I'm now going to restrict the discussion, just not to have to tell you what all of that is, to particular limits. So, so in principle, if you did this full model exactly for finite n and so on, you would be describing the extremal limit of this, which is some kind of geometry roughly like this. So finite temperature, a very long neck like this, like pinches of it's fine. So anyway, so it's a particular black hole, and if you could solve it for finite n and everything, it would give us the full quantum gravity theory. Now that's not the quantum gravity theory we understand. So it's, I think it's well defined, but we don't have an alternative definition rather than this one. Finite n. Now, when n is large and the temperature is relatively small, so what that means is that the temperature is smaller than the coupling. So remember, this has energy cubed. So when it's smaller than this, so that's the low temperature regime, and when n is much bigger than 1, then we can use classical gravity to discuss properties of this black hole. And we can then even discuss small quantizing the fields around this background, discuss corrections.
So I didn't understand this picture on the right. So you're saying even for finite n there would still be a geometric?
No,
picture,
no,
or
no,
what
because
is this?
yeah, so for finite, this picture on the right, yeah, this,
Okay.
well, the more correct thing is that, the slightly more correct thing is that at finite n, we should be doing a sum over geometries that, let's say near this region, has some fixed boundary conditions, and we sum over all possible geometries. Exactly which geometries we're summing and this sum is something we don't understand.
I mean, do you think that at finite n and finite temperature, I guess in the gravity picture, I would have thought that there's a near horizon region and an asymptotic region, but they can talk to each other in string theory. So you have to go to something that the coupling limit to just get that model or nothing else. Right?
Yes. I kind of glossed over this
Yeah.
a little bit. So I said that we go very close to extremality,
Yeah.
where we can forget about this flat space region and focus on like geometry like this. So that limit, we think it's well defined and supposed to be dual to this matrix model. So the matrix model is well defined without reference to any other theory, and we think that there should be a gravity theory which is well defined. That's dual to this. So in the Larsen limit, we understand relatively well what this geometry is for finite n and so on. We don't understand that. Now that this model is closely related to other examples of this type of dualities. Maybe you've heard about the ADS EFT dualities. So in this case, the model is not the conformal, so it's not an example of that, but there are higher dimensional versions of this model where it's related to anti-de Sitter space. Instead of anti-de Sitter space here, we have this other kind. And this geometry is some geometry where maybe I should be a little more not very mysterious, so but I'm not sure. Hopefully this will not be more confused. So it has there is a radial direction, right? There are some functions here that are all functions of R. So there is an 8-dimensional sphere some radius, and then there are well, some metric components in the time and space direction. Yeah, and in addition, the scalar field depends on R. There is some constant electric flux. Star 10 of F is equal to the volume form of the X here. So it's a, well, this is essentially the solution. There are specific functions of G. One particular point, just, well, maybe I'll try to, are there more
May I
questions?
ask you a question too? So here you have the theory of the gravity, you have the fields.
Yeah.
And the fields move in a curved space just based on the.
Yes.
But is there back reaction?
Yes, and so at infinite n, no,
But
at
within
finite
the-
n, yes. Here, of course, this is a curved geometry that comes from solving the full nonlinear equations with these fields. The nonlinear equations that come from this Lagrangian. But it's a relatively simple solution because all of the symmetries that you have, you can write it explicitly.
So the size of the S8, the S8 is of roughly the same size as the curvature radius of the.
Yes. Yeah. So there is, yeah, the size of the S8 is comparable to the curvature of the two-dimensional space, and this shape here roughly tells you what the size of the S8 is, the so-called string units. Yeah. So only when this size is relatively large, we can trust the geometry. So roughly speaking, so things that are so this function here is a function that is 0 here, and it increases as you go up. What that means is that there is a gravitational potential that pushes everything down to the horizon. Because normally the gravitational is a gravitational force that pushes everything to the horizon. And for that reason, if you have an excitation which has which has energy, let's say if you have some energy of order T, then it will be some excitation that lives around this region of the geometry. If it has energy much bigger than T, right, then you could live further away from the horizon. The particle that lives around here will have an energy much bigger than T. A particle that lives close to the horizon will have an energy of order T. In particular, if you have an energy of order, so energy of order lambda to the 1/3, right? That would correspond to a particle that lives in a region here. And beyond that, you cannot trust gravity. So gravity you can trust in some region, but in this regime, sorry, this is what I was calling lambda. We call this lambda. So there is a whole region where you can trust gravity. The bigger you make this difference, the bigger the region you can trust gravity.
Curvature radius, at least it becomes more curved if you go up. Or it becomes more strongly coupled. Both.
Well, what happens as you go up is that the Einstein gravity description becomes invalid because there are some light higher spin fields that are, so that the higher spin fields are becoming more important in this region. But I don't want to focus too much on this discussion. So maybe this whole geometry might sound a little confusing, and it is more confusing than other geometries we normally discuss. But it's somehow a necessary complication if we want to discuss at least the simplest known, let's say, quantum mechanical model, which is not the quantum field theory. So if we want to go to the simplest model, the gravity solution is a little more complicated than other examples. If you allow, yeah. So, and it has these small details of some regimes of validity, but those regimes of validity are kind of natural in some sense. If you have this model, consider this model at extremely high energies, it basically behaves like a bunch of free fields. And as you go to low energies, it becomes more strongly coupled. So in other words, if the temperature was much bigger than this, you can approximate this as just some classical, in terms of classical thermodynamics of working potential. But as you go to low temperatures, it becomes more quantum and harder to solve. And that's when you have the gravity description.
So what is then the rule that determines the boundary conditions that you need for the geometric picture? I guess you need some boundary conditions in addition to this. Do they come from this? How do they?
Yeah, so
rely?
okay, I guess you're asking me, how do we know that this, something like this is true?
Or is there a free, if you make this, let's say, duality, are the boundary conditions somehow fixed by
Yeah,
your description?
yeah,
of the
essentially the boundary conditions are fixed once you think a bit more about this, so.
So they're automatically fixed in a sense?
Yeah, essentially, yes.
Okay.
You have the option of changing them, and then that corresponds to changing the parameters of this Lagrangian. But let me say that there are some natural boundary conditions. Okay, so well, as you see, there are some complications, but I don't want you to live with the idea that this is a very complicated setup. It is really a very simple setup. It's only that I had a short time to discuss it, but it's not more complicated than a bunch of. I mean, if one says that one is going to simulate the most general complicated Lagrangian, right? This is a very simple Lagrangian. Zeroth order point.
So Juan, may I ask you something that, so I understand that you're imposing here that the gravity theory should be an Einstein gravity theory.
Yes.
Now, if you would relax that, could
Yes.
you simplify this? Namely, so is it expected that if you start this having some other theories
yes,
that are
yes,
much simpler,
yes.
then there would be some ways of connecting,
Yes,
and
yes,
this would
yes,
happen
yes.
for any theory?
Yes, okay, so let's go back here to the matrix model, to a single matrix model. The single matrix model has a gravity dual, but it's not in the Einstein gravity regime. It's in some kind of string theory regime. So it's a little harder to discuss. If we had to explain it, it would take me a little longer to explain exactly what this is.
Okay, so it is expected that there will be a series of models?
Yeah.
Many of them will not
For
have
example, the
anything to-
two matrix model that we can solve
Yeah.
is supposed to be, again, some gravity theory that involves some string theory of some kind. So the idea is that all these matrix models that involve matrices and this Larsen limit, they're all related to strings on some backgrounds. The problem is that we don't know how to solve strings in any of these backgrounds. We don't even know what the backgrounds are. So that's one point.
So when you
No.
use the term Einstein gravity, you meant, and there's a geometric picture.
Yes. By Einstein gravity, what I meant is that there is a geometric picture, and that the action is the Einstein. It's just the Einstein action, and that this is the length scales involved in this geometry are much bigger than L Planck.
Yes.
So that this action is trustworthy.
Okay.
So it's the simple case where we and that we know how to solve. So you have some particular theory, we can find the solutions. It's the solutions are written down and so on. So for example, as an example, I think I should mention that. For example, if you are in that regime, so as a function of the temperature, you could calculate, for example, the energy of this black hole as a function of the temperature. And you get some curves with some simple power law. That's fine, and there is no parameter in this power law. You know the convention, you know everything in terms of the parameters of the Lagrangian. And then, so there's a group of people who have taken this and made the Monte Carlo simulation of this model at finite temperature that involves taking this model and putting it on a circle, Euclidean circle like beta. So that's lattice type gauge theory, lattice computation, and they found some values, okay, and they look roughly like this. And so this is the temperature, let's say in units of lambda to the 1/3, and let's say one is roughly here, right? This is when the temperature for units of lambda to 1/3, so that energy scale that determines whether you're strongly coupled or weakly coupled is order 1. Then if you are above that, there is a big difference between the two. We didn't expect agreement. When it's below 1, it gets closer and closer to the curve. And the lowest point that they could do, let's say it agrees up to 7% with the gravity curve. Okay. So this is a parameter-free agreement. So it's some Lagrangian, some parameters, and you solve the theories this theory very concretely. Solve, find some number, solve here, find some other number, and they agree. 7%. We think the 7% has to do with partly the numerical error and partly that we didn't go to low enough temperatures. And so that's an example of which goes in the direction of checking this relationship. So
Is that an average energy for the thermal state?
yes, this is the thermal energy, not the free energy, but that's what they calculate.
Oh, that's
You can calculate the entropy here. Or some other. They find it easier to compute the energy. Okay. So now, and they did this with particular values of n. So in particular, this calculation was for n equal to 16. So this is just to give you an orientation of the type of numbers we are talking about. N equal to 16, and this value I think was 0.3. So it's not much more than 1. So they already see some agreement. So it kind of gives you a proof of principle that this can be done in a classical computer. Now, what would this be useful for? So I guess there's a question of what would you gain if you did it in a quantum computer? Now, this.
Sorry, I have just a minor question. So this has some zero mode when the matrices commute. So they must do something about that if they're, maybe they put on the math.
Yes, I ignored this issue, so.
Sorry.
No, but it's good, so I discussed in terms of harmonic oscillators, so there are actually some m squared terms and also some omega psi terms, but that gives some masses that remove the directions. And so the latest calculations here also have some value of this omega over t, which is some small number, let's say something like 0.8. So it's something small, smaller than 1, but not much. You would like this to be much more than 1, but you can find also what I didn't want to discuss this too much because then I would have to complicate this geometry a little more. So I think it was complicated enough, but the point is that there are kinds of checks you could do, but too complicated. I think something you could do with a quantum computer, you couldn't do with a classical computer. One thing is to calculate quasi-normal modes. So how, but maybe you can do also with a classical computer. So if you calculate the 2-point function of the form that we discussed here, this probably you cannot see here, but these 2-point functions go like e to the I omega t, omega nt can be decomposed in this way for large t. And these omega n's have a real part and an imaginary part. That the imaginary part is responsible for the correlation of decay, which is related to the thermalization system. And there's something, this form of the correlators, well, it's general to any system that has some self-interaction and it self-thermalizes. But there's something special about the systems we are discussing here, which is that these omegas are, for example, these imaginary parts are of order the temperature. So the lowest quasi-normal mode, so the lowest to thermalize very fast. They thermalize with the rate of order the temperature. So that's I think somewhat remarkable of this type of systems. It not be true of a system that lives in a lattice that might have conserved energy and hydrodynamic modes. It's not true of, let's say, the sun or a bell or any system that is made out of ordinary matter. These properties. In particular, this is independent of n, right? So if we make n larger, we don't make the thermalization slower. It's to be the same now. So I think this is something that is implied by the black hole, and perhaps can be, if we are searching over models and you have some model that you think might be a black hole, you can look for this and see whether has this property somehow. The thermalization is pretty fast and further the temperature, that's some evidence. is a black hole. Now, so of course, the geometry gives you a prediction for these numbers. So there is some sequence of numbers that you could then go and test. Now, but I think we should perhaps, there are a bunch of questions we can ask about. Well, there are questions about that you can ask about trying to simulate this model, and then there's some questions about trying to simulate models that have something to do with black holes. So we could discuss some of these questions. I guess the main question is what can we learn from this, or why might this be useful for? What might this be useful for? I think for me well, there are a bunch of things that this could be useful for. One is I think there might be a sequence. So I had here the SYK model and also this model, or you could say the one matrix model on one end of the blackboard, and this 9 matrix model on this other end. And you could ask, well, what are the models in between with maybe less matrices, or are they all, do they all have black holes? Do they not have black holes? What is the space of those things? So now, we have two conjectures, and I'm not sure. Well, let's maybe the string here is. So if you have some generic model in between with a bunch of matrices, so on, it could be that the generic model has black holes, or it could be that the generic model maybe it's not described by Einstein gravity. I'd like to know that. I think that would be interesting. So whether the generic strongly coupled quantum mechanics theory has a gravity dual or not. Maybe the ones that have gravity dual are very special. So, yeah.
Well, simulating the 2 matrix model of a quantum computer has got to be a lot easier than simulating this thing.
I agree. Yes, I agree. Yeah. So the only point to that's true. That's going to be much easier. And so that's why already there is an interesting question for the 2 matrix model.
But even for a classical computer.
Yes. Yeah. So people have done the free energy computation, for example, and when you get something, if you have just a 2 matrix model with these quartic potentials, at low temperatures is typically gapped. There is some large gap. That's what you find. So it's something special about this one that didn't have a gap, the large limit.
But this one, the supersymmetry seems somewhat important, right? Like, so, I mean, if I was a lazy experimentalist, I could say, let's just throw out the fermions instead.
Yes.
But that's bad, right? Because then you get negative
Well,
corrections.
you get the positive here, but yeah. So if you throw out the fermions, the same people who did with fermions did also without the fermions.
Yeah.
This model then would have a mass gap with a gap scale of order lambda.
I thought, okay, maybe I'm wrong, but I thought with the 0 mode, there are these 0 modes. Oh, well, so maybe with the mass fix is what I was going to say.
Yes.
Yeah, I was going to say without the mass, the 0 modes can bend down or bend up under Planck, correct?
They bend up.
Well, they bend
all
up.
bend up.
Yeah, they bend up for this.
Well, the Hamiltonian's positive, so they can hardly bend down.
Yeah. I guess that's true.
So yeah, so from there are some arguments that were made along these lines, saying that these models are special, that they have this large number of low energy states, exponential number of low energy states, similar to how the SYK model has this exponential number of low energy states, and that's certainly important. It's certainly important to get in the black hole, and that you seem to lose that if you just have lose the fermions. So maybe some form of fermions is important. They don't need to be supersymmetric. So maybe some matrix model which has one bosonic matrix, a couple of fermionic matrices, maybe to give you something interesting. And also there is the question of why matrices. I mean, it could be that you could have a bunch of fermions and bosons interacting in some way. But if the SYK gives us an example of models with only fermions. Yeah, so one question certainly we would like to understand is which models have an Einstein gravity description? As opposed to, and how to recognize that. Don't even as theorists, we like to come up with some criterion for recognizing when you have one. So I told you a little bit about the quasi-normal mode condition, but that's one condition, probably not sufficient. There are other more complicated things. I mean, if you do out of time order, and so the maximal chaos, that would be another delta signature having an Einstein gravity load. Yeah.
I have a question. Did the paper, I should maybe just look, if they throw out the fermions, is it still like a fast scrambler?
Yeah,
when
so
they
if
throw out-
you throw out the fermions, then you have the scale lambda, and the gap is of order lambda. And so the energy is much bigger than lambda, the system is more or less free. And the energy is much, temperature is much lower than lambda, you have a gap. And
Okay, so there's no thermal, it's fast thermal.
so there is no interesting regime where you have a thermal system that is strongly coupled. Sorry. So, but I don't know if they try to do. For them, it's hard to put the fermions, but maybe they could put the fermions without supersymmetry. Yeah, there are some questions. Yeah, so this is kind of an extreme example where we do know for sure that what we think we know for sure that there is a gravity dual, just to give an existence. But there might be all other kinds of things in between. Yeah.
So the model that you write down is actually very fine-tuned, you know, if one
Exactly.
to sort of build it and so on. So if one makes a mistake in some analog simulator with this fine-tuning, what's the consequence? How sensitive is it?
Yes. No, that's an excellent question, and yeah, so we can analyze a bit that question by thinking about the gravity solution. So there are some. Let's say we keep the SUN symmetry, but we add other terms to this Lagrangian. Then most of the terms become unimportant if we have this hierarchy. So they are, let's say, irrelevant in the renormalization group sense, except for a few that are not SO9 invariant. So there are a few terms that you would need to find. Then you would ask. I mean, for example, this mass square term is one of the terms that you could add that are important at lower energies. Then you could ask, what if you don't preserve the SUN symmetry? There, we don't know very well how to analyze it from the gravity point of view, but there are some more hand-waving arguments that if you break the SUN symmetry just a little bit, it shouldn't matter. But again, these are more hand-waving arguments.
I would have thought it's very important that it's G and G squared in those two terms, you know, with whatever the right coefficients. So if you mess up the normalization, that will already lift the zero modes and.
Well, no. So if these two coefficients are different, that would make would be some perturbation here, which is an irrelevant operator. So would not matter. So that we know.
So you say it's irrelevant. It's a SUSY breaking, but irrelevant.
Yes. So all SO9 invariant operators are irrelevant. The only relevant ones.
Sorry, but then why don't you say those terms are also irrelevant? I thought those terms are important and strong at low energy.
Yeah. So when we talk about irrelevant, I mean that if you make a little change, right?
Yeah.
And then if they will be relevant. But if you make a very big change, then I'm not making any. Yeah. So once you are somehow close to this, the basin of attraction, it looks like this is fairly good, and you could ask even more drastic questions, like saying, so this type of interactions, and I don't know the answer to this question. So this type of interaction involves many terms because you have to do all this matrix multiplication. It has for the n to the 4th terms. So even for a modest n like 16, you have a huge number of terms. And you could wonder whether you get the same physics if you throw away, let's say, a very large portion of these terms, let's say most of these terms. In the SYK model, people like I said, Edward and collaborators have discussed throwing away most of the couplings. As long as you keep a number of couplings which is of order n, then you can still get the same physics. So here you could ask whether that's true. Well, I don't know how to analyze that this problem. It is possible that you truncate it a lot and still maybe. Yeah, so I think, yeah, anyway, so well, we are over time. Well, maybe some of the other people who work on holography want to say what their favorite question is that they'd like to answer simulation.
We heard about entanglement Hamiltonian yesterday and some evolving by the entanglement Hamiltonian in some setups can like take you behind a black hole horizon. So maybe you could play around behind a black hole horizon.
Yes. Well, that's something interesting. Yeah, in general, I guess there's this idea that there is perhaps tensor network representation and maybe exploring that simulations. Interesting.
I don't know how to do it with this model, but if you could do n=4, it would be fun to learn about high energy string scattering in the regime where you don't make a black hole, but it's still strongly interacting, right? So we can learn what is string theory.
Yes, yeah, that's right. So I guess Daniel is more or less saying that we could explore this region here, the scattering of particles in this region, not related to the black hole horizon, and explore the short distance structure, the theory there. And that's true, yeah. In fact, already this calculation gives us a little bit of information about this, because this small deviation that you have here is related to a correction to this action. And they can calculate the effect of this correction by looking at this model, and it's something that hasn't yet been computed analytically, that we should be able to compute it in principle. So it's an example where the simulation actually is a little ahead of where we are with the analytic calculations here. So there is here a term that involves some corrections, some corrections of the form R4 with some coefficient. And, well, we don't know that coefficient for all the terms that are relevant involved in its rank and so on. Well, there is, of course, maybe the most interesting question is whether there is some quantum simulation we could do that represents not the black hole spacetime, but the cosmological spacetime. And we don't know how to start thinking about that. But let me put this as an interesting question. And there is a philosophical question that, well, maybe this is just for tea time conversation, but maybe after drink conversations, which is the philosophical question of whether if you simulate a black hole this way, you actually have a black hole or not. With that, I think I'll finish.